So last class we did, we finished the proof of density of primes between x by log x and 5x by log x, which also means that there is always a prime between x and 6x, and in fact you can strengthen it and say that there is always a prime between x and 2x. And then we started some applications in cryptography. Point of this will be that you will see everything that we have studied till now in number theory being applied, okay, in everyday use. So, any questions till now? Okay, so the way we model security or communication is that there are two players, Alice and Bob. So Alice wants to send a message which through this channel to Bob, which will be visible to others. For example, E is Eve. It will be visible to adversaries, but still the message should remain secret. Okay, so channel is, so basically the channel is like Wi-Fi or a cable which anybody can access. But still the communication between Alice and Bob should be private, right? That's the goal. So we model it by messages being strings of length small n. These are binary strings 0, 1. So clearly the message cannot be sent as it is, right? Because that will then be visible to adversaries. So you have to, Alice has to somehow encode it. So that is the encoding algorithm. So plain text becomes ciphertext. And there has to be a decryption algorithm which will convert ciphertext back to the message or plain text using a secret, right? So S is the secret which encoding, which encryption and decryption algorithms use. This secret is called secret because it will not be known to Eve and other adversaries. Okay, this has to be shared somehow between Alice and Bob only. So the most obvious encryption algorithm is this substitution cipher or Caesar's cipher, which is that if you are sending messages in English, you just transform the alphabet. So you, instead of A you use B, instead of B you use C, or any other permutation pi. That is the secret shared between Alice and Bob, not known to Eve. Right, so encryption and decryption are simple enough, but the problem with this is that it can be attacked and broken. So the idea was, how will Eve find the permutation pi? Yes, so assuming that Alice is sending a long text like a chapter of a book, of a chapter of an English book, right? So then it cannot have arbitrary frequencies of letters. So for example, E or A or what else? I. So vowels, for example, will be the first that you can decode, because the vowels will appear the most. Then the consonants, in the consonants also there is a frequency distribution that English has, assuming that the text is big. So using that you can reverse engineer pi. Okay, and once you have enough information about pi, you will be able to make sense of the ciphertext that was sent. So this is quite easy to break. So you have to do harder work. So the next example is block cipher. Which is a general term. So in here what you will do is that you will not encode at the level of letter. Okay, you will encode at the letter of block, at the level of blocks. So you, for example, you look at sentences which are 30 letters big, and you apply a transformation on them, you send it to some arbitrary string. Okay, so block by block, if you encode, then there cannot be any frequency analysis, because sentences can be widely different and they are being mapped to completely arbitrary strings. So whatever was the structure in the English sentence, it is lost, right? So this is a very general, I mean, I won't give a proper encryption algorithm, but generally what you are doing here is encrypting at the level of blocks. So divide the plain text into blocks of length k, each a string in 0, 1 to the k. So that is a block, and let me call it B. So each block is of length B, and so if you have the message length is n, then there are n by B blocks, and you come up with a complicated map which sends, let's say, the first block to something and second block to something. So it's again, you can think of it as a permutation, but it's a permutation on long strings, right? And then whatever is the internal structure of the language or the book, English book, that will be completely lost, as long as B is not 1. If you so previously we were kind of doing B equal to 1, because we were looking at letters and just permuting them. That was too weak. If you take B equal to 100, then you are kind of, it's like you are taking a paragraph and you are converting it into a completely arbitrary string, and then everything is lost. The structure is lost, it cannot be understood by Eve. That's the hope, anyways. So and so message in 0, 1 to the n is first seen as 0, 1 B cross n by B, and then encoded. Okay, so did we set some notation for ciphertext? Probably not. So let's say we just send n bits to n bits, and the way we will do it in block cipher is blocks of size B each, we will apply the transformation. Using some function f, which will have some secret s, let us say that we have this for simplicity. So the function that you will apply on a block is big F, and S is the secret which Eve should not know. and in the end you get the image, which you can then again concatenate, and you have the ciphertext. And obviously we'll take B to be quite large, right, because B equal to 1 was the Caesar cipher, which is easy to attack. So C is equal to F S comma M, okay, where M you break into blocks and then you apply block by block, and in the end you get C, right. That's the block cipher framework, but this is only a framework. The question is how will you actually implement this efficiently, right. So for that the function cannot be totally arbitrary, because if you are using, let's say, 100 size blocks, the number of such strings is 2 raised to 100. You cannot afford to just store a random permutation on this. That's too big, right. Then all the time you will need this space of 2 raised to 100, and that you want to keep it a secret, and you also want to share it between Alice and Bob. So all this will become completely infeasible. So you have to come up with a very clever F and a corresponding secret S. So there are many such clever block ciphers, which we will not do in this course. So there is what is called DES, digital encryption standard. There is AES, which is advanced encryption standard, and so on. There are more recent things like MD5. So these are basically functions, they are their definitions of functions F, which do a lot of algebraic manipulations, number theoretic and algebraic manipulations. It's too long to describe here, so I'll skip it. These are all algebraic. So they basically work in finite fields. They will add, they will multiply, they will divide, they will multiply by matrices, apply matrix transformations, and so on. And there are many levels. So after 10 levels of these complicated things, you get the C. So instead of getting into this, what we will do is we'll use the number theory that you have learned and give a much simpler but very highly applied, used everyday crypto system, which is public key crypto system, RSA. So let us, so this is used in all kinds of secure communication, like HTTPS uses this, SSH uses this, and so on. Also your phones, whatever they are, whenever they are saying, for example in WhatsApp, they are saying that it's secure, it's using RSA. So the goal here is slightly more complicated than the Alice Bob description. So here it will help to think of Bob as the bank. So this is, think of Bob as the bank and Alice as the customer of the bank. So there are many customers. So Bob, the bank basically wants to keep a secret which will never be shared with any customer. But still the bank wants the customers to communicate with the bank. So there is a message that Alice has, and she wants to send this in a secure way to the bank, and somebody else will send something else. Right, so customer A will send a message M, customer A prime will send M prime, and obviously none of them want M and M prime to be visible to anybody else. I mean, at least nobody else should understand the message M except the bank, because this is basically your account information, password, etc. Right? So these are very important things. You don't want anybody to know this. So what will be sent is obviously the cipher on the channel C and C prime. So how do you solve this problem? Because the main constraint is that there are millions of customers, and the bank cannot go and share the secret S with everybody individually, because that will be too expensive for the bank. The bank will become bankrupt if it has to talk to every customer every few weeks and share a secret, right? Because the secret then has to be different with every customer. There will be a different secret. So that won't be a business that can run forever. So the only thing that bank can do is publish something on its page, which everybody sees, right? And using that, the customers will encode and send the ciphertext. So there is something which is public. That's the public key. So this is common to all the customers, because it is the only way to access this is it is published on the page of the bank. And using the public key, the customers create the ciphertext and send it to the bank. And then the bank has a secret which will help the bank to decode. Right? That's the problem abstract model which you want to actually implement in practice. So what would this require? So clearly S cannot be P, right? It cannot be the same secret. S has to be different from P. So bank has to create two kind of secrets. One that will be made public to everybody for encoding purposes, and the other one will be only with the bank for decoding purposes. So two keys are needed. So one private, which is S, and the other public, which is P. And based on this, you have to now design encryption and decryption algorithms. Encryption algorithm will be used by all the customers, like you use in your bank, and decryption algorithm will be applicable only, can be used only by the bank. So this is a more complicated thing than the simple Alice-Bob communication, because there were only two players, but here there are millions of players other than the bank. So how do you think this is solved? What is done on your internet banking or your phone applications? Okay, so you don't know RSA then. So let's do RSA. So here let's set up the notation. So bank uses decryption with the private key, and the ciphertext, while the customer uses encryption with the public key and message. Right, so we have to design these two practical algorithms, which then accordingly we have to design, the underlying secret and private keys. So the requirement is that S or knowing P and C, one can neither get S nor M. Right, so remember that an adversary, if A was U, then the adversary is able to see both C and P. Right, so both the ciphertext and the public key are visible to the adversary, and from that, adversary should not be able to deduce. Even over days or years, let's say for 1 year, the adversary keeps trying, looking at your messages, but he or she should not be able to deduce neither the message that you sent nor the secret of the bank. Obviously, if the adversary can find the secret of the bank, then the bank completely collapses, because then all the accounts in the bank have been hacked. Right? That's a far more serious problem. But even a single M for a single customer should not be deducible. Right? That's the tough requirement. So obviously P and S has to be different, but they have to be kind of completely uncorrelated. So this problem was solved in 1977 by Revest, Shamir, and Adelman. If you go outside RM 101, you can see their pictures after the class. So this is why it is called RSA. So they constructed or designed with such PNS. Okay, such that P will help everybody to encode, but will not tell anything about S, and obviously will not tell anything about the message, the plain text. So this is the most famous crypto system. So this is completely based on number theory. Let's see the steps. So first is the key generation step. How does the bank come up with the keys? So the bank picks two prime numbers which are quite large. Primes P and Q, which are distinct and they are quite large. So you use them around 800 digits, around 400 digits. Okay, which means it's around, the value is around 10 to the 400, it's in base 10. So extremely large primes you find. This is easy to find because of the estimate we proved. right? If you just randomly pick a 400-digit number, with good probability, it is a prime number. It's not composite. How do you find out that it's prime? How do you confirm? So there are many primality algorithms which you can study in advanced courses. Yes, you wouldn't want to use AKS, but there are much faster algorithms which are used. So they are probabilistic algorithms, but they are very practical. So you basically guess and then verify probabilistically. So the guessing part is fine because we have seen the estimate, so you will be able to easily guess a prime number, but then you have to verify that it's actually prime. So that needs more advanced number theory algorithms, and that you can study separately. It's not in the course, but this can be done. So the bank finds this PQ, and then based on the primes, the number n is P times Q. Okay, this becomes public key. This is what is sent to all the customers, the number n. So number n is around 800 digits. Now you can ask, why can't an adversary just factor n and find PQ? And then the bank crashes. Right? You can do this now. I mean, you have many bank accounts, and the bank has sent you this n, you can just factor it. Is it possible? Sorry? Yes. No, you think about a number which has 800 decimal digits. There is no way to factor it. If you went through, the only way is exhaustive method, and that will require you to search for 10 to the 400 steps. Right? So that is again much more than the age of the universe or the future of the universe. So you cannot do these things. So that is why it is believed to be secure. There is no algorithm to factor this practically. You can spend years on this, but still you will not find a factor. So that is the basic security premise here. Everything else is details. So the thing is, how do you use this number n to encrypt? Or how will the customer Alice encrypt the message using this n? Do you know that already? How is encryption done using n? It's modern arithmetic. So what is done is that Alice will just exponentiate m with e, where e is another public information that bank sends. So Alice computes m to the e mod n. Okay, just as simple as that. So for which e also has to be published. So also publish an e. Pick an e co-prime to phi n. The Euler-Tauschent function, and publish them. So n comma e you publish. The bank publishes. That's the public key. Okay, so bank claims, announces that modern arithmetic will be done, and exponentiation will be done of the message by e. So this everybody can do, right? Now you see this phi n sitting there. which was a very exotic thing we had defined in the previous classes, right? So why is that appearing here? But before that, let's see encryption. Just let's specify encryption. So encryption is done by Alice. So the ciphertext that is computed is m to the e mod n. And transmit this. To Bob. Okay, so customer just encrypts the whatever the message is. This is the password, the account number, this much money has to be transferred. Right, that's the message. You look at it as a, let's say, number. The whole message, you think of it as a number modulo n, and you raise it to e. Okay, so you will get another number which is in the same z/n set. So it's between 0 to n minus 1. And you send this number to the bank. Is this fine? That's all encryption is. So how fast will you be able to do this? Yes, so E I should have said is, I should give the parameters. So E is between 1 and phi n. Right, so in particular E is also smaller than n, which means that it is around 800 digits, but I think it is taken smaller than 800 digits. There is no need to keep this complicated. So say E is 100 or 200 decimal digits. And then computing m to the e mod n is this, you use the repeated squaring idea. So maybe I recall that. So write e in base 2 and use repeated squaring mod n. So roughly speaking, this will take log of e steps. And there is also mod n arithmetic, so that's another log n. Okay, so thing is not, it is not very expensive. It's also not completely cheap. So log e is around, sorry? Yeah, so log n is definitely 800, around 800. It's actually more because in base 2 it will be, so this is base 2, right? So if you want to be very exact, then this will be around 2000, I guess. So this is 2000 square, but 2000 square is also not too much. That for loop you can run in few seconds, or few milliseconds even. So, sorry? No, because there is also this mod n computation is division. So it's more than actually log n, it will be around log square n. No, but sure, but what is mod n? Mod n is division costs. If you do it by long division, in the high school method, if you have 100 digits, you will have 100 steps. So it's actually more than log n, but I am just giving a very rough estimate. So this is around that much. So you can think of it as 2000 square or 2000 cube. Even 2000 cube is not expensive. It's a for loop with these many steps, so you can compute it. That is what Alice will do and will get the ciphertext. So which is why all your bank transactions are very fast, because this is being done almost instantly, this exponentiation modern. And so the question at this point you have to ask is, this C and N and E is visible to the adversary, right? Your friend who wants to hack your account. So why is he not able to compute M? Right? E is known, N is known in this equation, and C is also known. It's only M which is unknown. So why can't your friend solve for M as fast as you have encoded? Sorry? Cannot hear. No, I meant why can't somebody just say C to the 1 over E mod and compute that? I mean, we know how to compute square roots and cube roots and fourth roots. So why can't you just compute 1 by Eth root? Sorry? Yeah, so the problem is that it's not, suppose E was 2, even in that case, you have to, your adversary has to compute square root of C, but it's not just square root of C, it's square roots of C mod N. There is no algorithm for that, except that you have to factor N and then do other things, which I cannot discuss here. But all those things are much more complicated than just computing square root. Okay, it's not square root of an integer, it's square root of a residue. That there are no fast algorithms for doing that unless you factor in. So adversary has your ciphertext N and E, yet cannot find M by any known fast algorithm. Okay, that is what the current status is. There is no way to solve that equation for M. Out of 4 things, 3 things are known. Okay, so then adversary cannot do anything. For adversary, ciphertext is just C is just a string of 0, 1, which is kind of a random object. Adversary is unable to learn anything about your account or password or whatever. No useful information is obtained. Then the bank receives it, and the bank now has to make sense of it. So how will bank compute M? How will bank solve this? Yes, bank has P and Q, but I want still a simple algorithm. I don't want you to give me a complicated algorithm. It should be a straightforward algorithm. So what is a straightforward algorithm for the bank? So what bank will do is compute inverse of E, mod phi n. Okay, that is another major theorem we proved in the last classes, which is Euler's theorem. So compute D, which is E inverse mod phi n. This thing will exist because that's why I assumed E co-prime to phi n. Okay, since E is co-prime, so E inverse will exist. And this D is then used as follows. So C to the D mod n is computed. What do you think it will be, the value? Yeah, so it happens to be m. That's the beauty of number theory. So this is equal to m. So it's very easy for the bank, just kind of a reverse computation is done and bank gets the message back. Which means that if D was known to the adversary, then adversary can also do the same, right? So the question is, can adversary find D from C, E and N? So what is D? D is defined to be E inverse mod phi n. So E is known, N is known. Why can't the adversary compute phi n? Sorry? Yeah, that is, yeah, so the first answer will be that, but it's not the complete story. I mean, you can actually formally show that if the adversary can compute phi n, then adversary can factor in. Okay, there are these results. So, I mean, even if the adversary is very smart, still computing phi n will be like factoring in. That is known. If the adversary is not smart, then from n computing phi n will take, it's basically enumeration of numbers. So numbers are 10 raised to 800. So again, enumerating that is extremely complicated. I mean, extremely long time process. So yeah, either way it will not work. One has to factor in. Okay, so all we have to now check is this C raised to D thing. So C raised to D is m raised to ed. What is ed? 1 plus k phi n. And what is m to the phi n? Yeah, why is it 1? I mean, it is 1 in Euler's theorem only when m and n are co-prime. Maybe your message, your password is such that it shares a factor with n. If it shares a factor with n, then your password is actually factoring n. So you as a customer has already crashed the bank. Can that happen? Oh, no, so everything here is happening 1 to n minus 1. Everything is log n bits. I mean, everything is 800 digits. So can it happen that your message shares a factor with n? Yeah, so that is a risk which the bank is willing to take. So the bank just hopes that there will be no customer and no adversary who can pick a message which factors in. Okay, all the banks run on this faith. Everything has worked fine till now. So let's just use Euler's theorem here and you get mod n. So since m and n are co-prime, and then we are applying Euler's theorem. And E inverse is Euclid's GCD. And what is phi n? How did bank compute phi n? Yeah, bank has primes, so it is just p minus 1 times q minus 1. It's already known to the bank. So that is just multiplication. And E inverse mod that thing is just extended Euclid GCD. Then C raised to D is again just repeated squaring. And in modern arithmetic. Right, so everything here is easy for the bank, and bank gets your message back. Right, so this covers all the results that you had seen in the chapter on number theory. Any questions? So that is how you communicate with your bank, and HTTPS and WhatsApp. Every WhatsApp message that you send is based on this. Any questions? Okay, so I guess simultaneously we have discussed efficiency and security. Every step you can see is efficient, and security is based on, let's write that down. So key generation, encryption, decryption are efficient, and RSA is secure. Based on the assumption that n cannot be factored. And this C to the 1 by E mod n can't be found. So the first question is the integer factoring question. There are no algorithms for integer factoring which can match practice. And the second question is called is it the discrete log question? No, this is just the radical computing question. So that also we are assuming it's hard to do. Yeah, so these are the two assumptions on which the security is based, and there is very little progress in these two questions. All the progress is below 800 digits, which is why we set 800 digits. If you use 500 digits, then there may be attacks. Okay, so generally applications use 800 to 1600 digits. Then it becomes intractable to attack. Actually, there are more things here, so we are also assuming that phi n computing is hard. Because if adversary given n can find phi n, then the adversary can find D, which is E inverse. Right? So if the adversary finds D, then again the bank completely collapses, because then anybody can do what the bank was doing. But this is not a problem. Actually, the third assumption relates to the first assumption. They are equivalent. So that I leave as an exercise. It's only for the advanced students. So an algorithm, fast algorithm for phi n implies algorithm for factoring. So, and it's equivalent. So there are only two assumptions effectively that gives the security of RSA. There is one more exercise you can try. That if P and Q are very close, which means P minus Q is very small, then they can be found, then n can be factored. Okay, in particular, suppose P and Q are twin primes, right? Q is P plus 2. So the difference of them is just 2. Can you factor n in that case? Right, because you set up a quadratic equation. P times P plus 2 is equal to n. And from the quadratic equation, you will find P. So the same thing works to some extent. Assuming P minus Q very small, you can easily use that idea to factor in. So that is avoided in the RSA specification. You take 400-digit prime numbers, but they should be far away. Say the difference between them is also 300 digits. Right? So then they are very far, and then there is no hope. So this encryption algorithm, since you want this to be used in small devices, like also smartphones, so you don't want encryption, or you want encryption to be as fast as possible. So for that, E is picked, you can pick E to be small. So that will make encryption fast. But when you take E small, then E inverse can be anything. In particular, it will be quite large. So it will become expensive on the bank side. So what the bank can do is, bank can do Chinese remaindering. So B can use Chinese remaindering. So basically mod P and mod Q. To compute C to the D mod n. So that will be at least twice as fast, because n is 800 digits, while mod P it's only 400 digit calculation. So it's actually faster than 2 times. So you compute mod P C to the D, and you compute C to the D mod Q, and then you can combine the answers by Chinese remaindering to get mod n answer. Okay, so even Chinese remaindering is applicable here in the practical implementation. So the bank can also use a faster decryption method. Although this is not very important because bank has unlimited resources. But the first thing is more important, so you pick E to be small. Okay, so any questions at this point? Fine, so now you know this and you know how important it is. So you can think about how to attack it, right? Your safety of your money depends on this. Yeah, so these applications and other applications motivate us to move to more advanced areas. So the next area will be algebra, and in that we'll study finite fields first. So I think from now on we will only study algebraic objects, and we'll start with fields because field is something which you have already seen. So all the arithmetic that you do is generally over a field. So in particular, this you have already seen that for prime P, this set that we defined, Z mod P or Z slash P, elements 0 to P minus 1, it has a lot of properties which integers or fractions have, right? So you can do addition here, you can multiply here in the set. Did we also see division? We also saw division, right? Because if you take any element A in this, A inverse exists, 1 over A exists. So you can also do division, except for A equal to 0, of course. So this set affords addition, multiplication and division. Right, where division by 0 is not allowed, but everything else is allowed. So that's like what you are used to in numbers, right? Integers, rationals, complex. So Z slash P is like that, but smaller, right? And it comes in many shapes because as you change P, the arithmetic changes. So it is in a way a richer family than the set of integers. So this kind of objects, we want to give them a name, that will be field. So it behaves like integers, reals, rationals, and complex numbers. Yeah, before I define that, let's see a set where this is not possible, which is not as rich as this. So suppose I look at Z mod P star, right? So I remove 0. So will it have all the properties which we listed above? Can you add here? Why not? 1 plus 2 will be 3. Those things are there. So how is it different from Z slash P? Sorry? N minus 1 and 1, yeah. So you can, okay, so let's do this step by step. So first counter example is addition. Addition is absent because P minus 1 plus 1. So both 1 and P minus 1 are elements, but the sum is not. right? So which means that it is the addition operation is not for free. You slightly change the set, and then you cannot really do addition because you will go out of the set. And obviously, if you make the set smaller, then it will only get worse. So addition goes out. What else goes out? Can you multiply? Yeah, so this set is still very nice in the sense that it still affords multiplication. Any two things you multiply, you can get a representative for the product in the set. So multiplication is there. And what about division? So division is also present, because division anyways in Z/P was because of, after removing 0. So if you remove 0, that property is still there. And what happens when you look at Z/n where n is not prime? What happens with composite n? Can you add? Can you multiply? Yeah, so addition multiplication is still there, but division is absent, right? Because as we have seen many times before, you take Z/4, so then 2 inverse is not there. It doesn't exist. So only division goes out. Right, so you can come up, basically for any combination of these properties, you can come up with an example. Example of a set where you will have one of these things or subset of these things, but not everything. And when you have everything, then it is somehow very special. Something like Z/P or reals, rationals, complex numbers. Can you divide in the set of integers? Obviously you cannot, right? 1/2 is not in the set. So integers is kind of a weaker set here, but all these other things, reals, rationals, complex, Z/P, they have division, they have everything. So that is what we call a field. These are examples of field. Let's define it next time.